Alrighty, so like I was saying, today you're going to learn about two new types of intervals. They're called a one sample mean Z interval and a one sample mean T interval. So those are the two that you'll learn today, and it's chapter 22 in your book if you want to read through it. So again, let me take you through the steps of making any interval ever. You first have to define your parameter. Then you have to check some conditions. Then you have to use the formula to calculate the interval. Finally, you have to interpret your interval. And then sometimes it's going to ask you to interpret the confidence level. So we are moving on to what's called a mean interval. So that means your variable is the average test score, or the mean height, or the mean weight. So we're moving on to a new variable. So here's how you define your parameter now. We're not going to be using P for the parameter anymore because it's not a proportion. Now we're going to use this Greek letter M. It's called mu. And that stands for the true mean, and then ... like the true mean test score, or the true mean age, or the true mean income of Americans, or whatever. So that's your new parameter. So make sure you know that. You would see this as a multiple choice, but make sure you know to select the one that has the mu now instead of the P. Next, the conditions are almost the same as before. The first one is the same, randomization condition. The second one's also the same, the 10% condition. Okay, oh, and there's supposed to be a PowerPoint to this, sorry. Okay, the third condition is the one that's different. So we're moving away from proportion. So we're not going to do the n times p is at least 10, or the n times q. We're moving away from that. So here's how you're going to check the third condition for the large enough. You have to check it by either the problem says that the population is normal, so you would say that, or your sample is at least 30. So if your sample size is at least 30, you can say the sample is large enough because of the central limit theorem. Or the last option, which I think we're going to do next chapter, sometimes you have the data and you have to graph it, but we're not going to do that one today. So today we're either going to say the sample is large enough because the problem says population is normal, or we're going to say it's large enough because our sample is at least 30. So that's the new condition that you need to check. Okay, next, you have to know, okay, there's two types of intervals that we're going to be making today. And the two types depend on whether you know the standard deviation of the population. First of all, that's called sigma. So if you ever see this Greek letter S called sigma, that stands for the standard deviation of the entire population. So if you know that, you will do what's called a Z interval. And I'll show you on the calculator. Next, if you do not know sigma, so if the standard deviation of the entire population is not known, we do what's called a T interval. And in that case, instead of knowing the standard deviation of the entire population, you'll just know the standard deviation of a sample. And again, I'll show you an example in a minute. Okay, here are the formulas. So if you do know sigma, which is the standard deviation of the whole population, this is the formula that you're going to use to make your interval. You're going to take the x bar, which stands for the sample mean, plus or minus your critical value times sigma over the square root of n. So that's the formula, memorize it. If you do not know sigma, here's the formula. We're still going to do x bar, so the sample mean, plus or minus, okay, now we're going to change our z star to something called a t star. That's a t score, and today I'm going to talk to you about them. And that's why these are called t intervals, because they have a t here. Times S here, that stands for the standard deviation of the sample only. So this is going to be standard deviation of the sample only. Oh yeah, S equals standard deviation of the sample divided by the square root of your sample size. So those are the formulas. And then the rest is the same as before. You do need to interpret your interval with the wording recipe. we are blank percent confident that the true mean blank lies between blank and blank. And then finally, sometimes it's going to ask you to interpret the confidence level. So that wording recipe is the one that says, using this method, blank percent of the time, the intervals constructed will contain the true parameter. And this time, the parameter would be the population mean. Because like I said, we're moving away from proportions, and now we're going to be doing mean. So your population mean. Pause for questions. Okay, so I guess now that we've gone over all this, let's go ahead and try our first example. Number 1. So it says a test for the level of potassium in the blood is not perfectly precise. Suppose that repeated measurements for the same person on different days varies normally. That's going to be important for our conditions, with a standard deviation of 0.2. If 3 measurements were taken on different days with a mean of 3.2, what is a 90% confidence interval for the mean potassium level? So here, like, you're interested in knowing the true mean potassium level, I guess, of a person, but you can't just take infinite samples from the person. So instead, we're going to use the 3 measurements that were taken, and we're going to construct an interval. So now here's the hint. For this problem, the standard deviation of 0.2 that was given, that's for the entire population, because it was given to you like at the very beginning where it says like the population of measurements is normally distributed with the mean of 0.2. So that means that, with a standard deviation of 0.2. That means that this standard deviation of 0.2 applies to all measurements. So in other words, this is called the standard deviation of the population, sigma. So therefore, we will do a Z interval. So first accept that, and now let's follow the steps. Step 1, define the parameter. Okay, go ahead and here, practice defining the parameter. Make sure you use mu instead of P. Mu equals. You would see this as multiple choice on your test, next test or quiz. So I started with mu equals the true mean potassium level of a person. So mu equals true mean potassium level. Write it down or type it up on your notes. Second step, check all the conditions. So these you would have to like type them up, I guess, if I ask you as for a response, or sometimes they're multiple choice. So the conditions would be randomization condition. Assume that the measurements, the 3 measurements, assume that those are a random sample. 10% condition. Assume or surely 3 measurements is less than 10% of the possible population. So basically for this person, they only took 3 samples of their blood. So we're going to assume that those 3 samples are less than 10% of the possible measurements. And we're going to assume that those 3 samples are random. Now, finally, check the new one, the large enough. And again, you're not going to do the success failures anymore because this is not a proportion. For the large enough, either the problem says your data is normally distributed or your sample has to be at least 30. The good news for this one is that the sample of 3 is large enough because the problem says you have normally distributed data. So in other words, 3 is large enough because the population is normal. That third condition, it's called large enough, or sometimes it's called nearly normal. I don't know if I wrote this on the notes over here. Large enough condition. Yeah, over here it says large enough or nearly normal. Either one, it's the same thing. So the sample is large enough because the population is normal. Done. So step 1, done. Step 2, done. Step 3, let's use the correct formula now. We're going to be using a Z interval. And like I said, get your calculator ready because we're going to use a calculator. But here's how you do a Z interval. You start with the formula. X bar, which stands for the sample mean, or the mean in this sample of blood, plus or minus Z star times sigma over the square root of n. So we're going to start substituting some numbers here. So here the sample mean is going to be the number that was giving of 3.2. That was the mean potassium level in the sample of 3. So this mean of 3.2 is what I'm going to replace the X bar with, 3.2. Okay, that's incorrect right there. Next, my inverse. Let me fix this one. This should be inverse normal. Normal. Okay. Comma 0. Come on. Okay. Let's bring it back. Okay, this is I'm fixing it. There we go. So since this is a Z interval, you're doing a Z star like you used to. It's called inverse normal. And then, although it's a 90% confidence level, remember that you have to add the lower tail. So you're going to do inverse normal 0.95, comma 0, comma 1. The sigma is the 0.2, which was the standard deviation of the entire population. So put 0.2, divided by the square root of the sample size, so 3. Now, I'm going to go ahead and just use the calculator to get your answer. So I'm not going to really type the 3.2 plus or minus. What I'm going to do is I'm going to go find something called a one sample mean Z interval. So practice finding that on your calculators. Calculator. You need to go to menu. Go to statistics. We're going to be doing the confidence interval. Our next lesson will be the test. But for now, go to menu, go to statistics. Go to confidence interval. Okay, so here's the one you need to pick. Actually, it's called Z interval, your first one. It's called a Z interval. So remember that you've already done like the 1 proportion and the 2 proportion. Today, you're going to learn about the Z interval and the T interval. Those are for means. Go ahead and click on the Z interval. Next, it's going to ask you for the data. So if you had a list of your data, then you will go here, data, but you don't. So switch that to stats. So switch this thing to stats and press OK. And now type in the info that you know. We know that the standard deviation of the potassium level is 0.2. We know that the sample, the mean from this specific sample was 3.2. We know that the sample size was 3. And we want a 90% confidence level. And if you do that, it's going to give you the interval that you want. And you can just copy that. The interval goes from 3.01 to 3.39. So copy that on your paper. We'll practice it again. So 3.01 to 3.39. Make sure you round correctly on the test. If I ask you to 2 decimal places, just follow directions. So that's how you use the calculator to get your interval. Now you need to interpret it. So you would say something like, I am 90% confident that the true potassium level in the blood lies between 3.01 and 3.39. So that's how you would interpret it. Again, I think that would be multiple choice on your test and quiz. And then the final step, sometimes it's going to ask you to interpret the level. So this is a 90% level. So you would say, like, using this method, 90% of the time, the intervals constructed will contain the true population parameter, or you can put population mean. I'm going to pause for questions. Okay, so now that we've made the interval and interpret the interval, apparently there's a part F and G. Part F. And this goes back to chapter 20. We've done this before. Using your interval, you can reject or fail to reject a null hypothesis. So let's try it. Letter F. Using your interval, is there enough evidence to conclude that the true mean potassium level is more than 2.9? The answer is probably going to be yes, because remember the interval was more than 2.9. So here's how you explain it. Step one, it would be helpful to write some hypotheses. And we will do more hypotheses on our next lesson where we actually do a whole test. But the null hypothesis for this scenario would be that the potassium level is equal to 2.9, or you can put mu equals to 2.9. And remember, mu is the mean potassium level. The alternative is you're looking to see if the potassium level is more than 2.9. So that's your alternative, more than 2.9. Now, here's how you use your interval to analyze the situation. If your null hypothesis of 2.9 is contained in the interval, then you do not reject the null hypothesis. But if your null hypothesis, which is 2.9, is not contained in the interval, which is our case, not contained in the interval, you can reject that null hypothesis and conclude that HA is true. So again, remember your interval was the interval was 3.01 to 3.39. So since 2.9 is not in this interval, you will reject the null hypothesis of 2.9. So since 2.9 is not in the interval, I reject the null hypothesis. There is evidence to suggest that the true mean is more than 2.9. And the reason why is because, it's like what I said here, we can conclude that the mean potassium level is more than 2.9 because remember that we are 90% sure that the true potassium is somewhere between 3.01 and 3 point something. In other words, the entire interval is more than 2.9. And again, that's chapter 20. If you need to practice that, go to read chapter 20. And then finally, the significance level. It helps if you draw a picture to help you determine the significance level. But this interval was 90%, so that's what I put in the middle, 90% interval. That means that there is 5% on each of these tails. And since your alternative is just a greater than, that means you only want the upper tail. So that's a 5% significance. Okay. Questions? Overall questions about number one. Okay, I'll give you a minute to finish writing everything you need to write. I don't want to pause the video, so we're just keep moving. So that was number one. Oh, okay. The hardest part on this unit is for students to determine whether you're doing the Z interval, like we just did, or the T interval. So, I changed number one, like I changed the wording of number one to make it a T interval instead. So here's what it would look like. So number one, if it said something like this, a test for the potassium level in the blood is not perfectly precise. Suppose that the measurements vary normally. Okay, so now it says if 3 measurements are taken with a mean of 3.2 and a standard deviation of 0.2, that would make this a T interval because this standard deviation of 0.2 only applies to the 3 measurements. So the standard deviation of 0.2 only applies to the 3 measurements. So I guess you're gonna have to like read the scenario, read the wording, and determine like where that standard deviation is given. Because remember that 0.2 was originally, this 0.2 was given at the very beginning for the entire population that was normally distributed. Here I changed the order. I put it as the 0.2 is the standard deviation of just the 3 measurements. It's okay. We're going to have to practice for you to determine between a Z and a T. Okay. Now let's try number 2. Okay, obviously number 2 is going to have to be a T interval because we already did a Z interval. But let's read number 2. Problem number 2. A nutrition laboratory tests 40 reduced sodium hot dogs. So these 40 hot dogs have a mean of 310 milligrams of sodium with a standard deviation of 36 milligrams. So this is what I was trying to say. This 36, the standard deviation here of 36 milligrams only applies to the 40 hot dogs. So that's what's called a T interval. So since the standard deviation of 36 only applies to the sample of 40 hot dogs, we're going to do a T interval. So get your pencils ready and let's try a T interval. It's going to be the same thing. Everything's going to be exactly the same except for the formula. So let's try it. Step 1, define the parameter. So either write it down or type it up, I guess, on your Word document. The parameter is going to be mu, which is the mean, equals the true mean sodium level in hot dogs. So step 1, done. Step 2, you're supposed to check some conditions. I think I already wrote him down on here. Yep. Randomization condition. Assume we have a random sample of 40 hot dogs. 10% condition. Assume that 40 is less than 10% of all hot dogs. Now, large enough condition / or you can call it nearly normal. For this one, although the problem doesn't say you have normally distributed data, since your sample is at least 40, so that's at least, since your sample is at least 30, it will be large enough because of the central limit theorem. So that's how you can explain it. If it's free response or if it's multiple choice, select the one that sounds like this. Since 40 is greater than or equal to 30, the central limit theorem says your sample is large enough to use the normal model. So everything so far is the same as the Z interval. Define your parameter, check your conditions. Here's the difference. Now we need to do the formula for a T interval. Memorize it, write it down. The formula is X bar plus or minus T star. So now we're going to use something called a T star or a T score times S, which will be the standard deviation of the sample only, divided by the square root of N. Okay, so now I would write this down for your work so that eventually you come back and study it. So here's how you substitute. X bar would be the sample mean. So in the sample, what was the mean sodium? It was 310 plus or minus. Okay, now we're switching from, instead of doing inverse normals for the Z scores, now we're going to switch to something called inverse T for the T scores. So write it down, inverse T. I'll show you how inverse T's work. Since this was a 95% confidence level, I'm going to go ahead and put 0.975 here because you have to add the bottom tail area. So put 0.975. Comma 39, I'll tell you where that comes from. But basically, I took the sample of 40 and I subtracted 1. I'll tell you about it. Next, S would be the standard deviation of the sample. So that was 36 milligrams divided by the square root of 40. Okay, let me show you how to use the calculator to get the answer. And then I'll tell you about this inverse T situation. On your calculators, go find the intervals menu. Stat intervals. Okay, this time choose the one that says T interval. Choose the one that says T interval. Again, you don't have the whole data, so switch that to stats. And now start typing some things. So the mean sodium level was 310 The standard deviation was 36. The sample was 40 hot dogs, and the level was 95%. Press OK, and it's going to give you the lower bound and the upper bound of your T interval. You just copy that, 298.49. You can round to whatever the directions say, and 321.51. So that's the sodium level in these hot dogs. So write it down. I rounded to one decimal, so 298.5 to 321.5. And if it asks you to interpret it, you would say we are 95% confident or 95% sure that the true potassium level of all of the hot dogs is somewhere between 298.5 milligrams to 321.5 milligrams. So the procedures for a T interval and a Z interval are exactly the same. Like same procedures, same everything. The only difference is the formula and using this inverse T situation here. So I need to show you how to do that. So on your notes, we are on interpret your interval. So I just did. We are 95% confident that the true mean sodium level lies between 298.5 and 321.5 milligrams. And then it asks you to interpret the level again. So using this method, 95% of the time, the intervals constructed will contain the true population parameter, or now you can say the true population mean. So those are still the same as always. We can skip letter E because it's the same thing. Okay. Oh, I guess there's an F and a G. So do them again, I guess. Sure, let's just do them again. So using the this interval, go ahead and tell me, is there evidence that the sodium level is less than 300 milligrams? Less than 300 milligrams. The answer is going to be no, because although your interval does go to less than 300, it also goes to more than 300. So it's possible that the sodium level is like 320 milligrams. So letter F, is there evidence? Explain using your interval. First, we write some hypotheses. The null hypothesis would be that the sodium level is equal to 300. The alternative would be that the sodium level is less than 300, because that's what you want to test. Based on your interval, this time 300 is contained in my interval. So when the null hypothesis is contained in the interval, you do not reject the null hypothesis, and therefore don't have enough evidence for HA. Or in other words, since 300 milligrams is contained in my interval, I failed to reject the null hypothesis. There is not enough evidence that the true sodium level is less than 300. Okay, I'll give you a minute. I'm going to pause the video, give you a minute to write all of this, and then we'll finish off the notes. So let's finish off today's notes with learning some facts about a T distribution and how to do that inverse T thing that was for the T interval. So on your notes, you have like all the facts and you have some pictures there that you do need to understand. And then we'll have one example. So basically, here it goes. You already know about a normal distribution. It looks like a normal curve, and you know how to do normal CDF in inverse normal. Next, you're going to learn something called a T distribution. So it says when we substitute S for sigma, so the standard deviation of the sample instead of the standard deviation of the population, then we no longer have a normal distribution, we have a t distribution. So here's some facts that you need to know about the t distribution. Memorize them. Number one, it is a symmetric graph that's centered around 0 and it looks bell curved, like bell shaped. Number two, it has more area in the tails than the normal distribution. So here's a picture to help you with that. So I know the two curves look the same. They look like a bell curve. This solid line here, that's called a normal distribution, and you're used to that one. Okay, the other bell-looking curve that's dashed, that's called a t-distribution. Obviously, it looks almost the same as a normal, except for if you notice in the tails here, like the lower tail and the upper tail, the dashed line is wider in the tails. So that's what it means that it has more area in the tails than the normal distribution. You need to know those facts. There's concept questions about it on the AP exam. So here, like the area for the t-distribution in the tail here is larger than the area for the normal distribution. So that's the second fact. The third fact, t-distributions have something called degrees of freedom. Memorize it. It's n-1, where n is the sample size. As those degrees of freedom increase, the t-distribution looks more and more normal. So let me show you a picture for that one. Here we go. So all these little graphs here, they're all t-distributions because they all look like a normal curve. They're called t-distributions. This red one here is degrees of freedom 3. The next one is the blue, degrees of freedom 6. As the degrees of freedom increase from 3 to 6 to 10 to 100 to 1,000 to infinity, the t-distribution becomes more and more exactly like a normal curve. So make sure you know that. As the degrees of freedom increase, the t-distribution becomes more and more like a normal distribution. So memorize the facts. They're on your notes. Just memorize them. They're right here. Memorize them. Okay, so now let's do the last example. You need to practice finding like inverse t's. So you already know how to do like the z star by doing an inverse normal. Okay, this time you need to practice finding a t star by doing an inverse t. And here's what you'll need. You'll need the calculator, obviously. When you do an inverse t, you're still going to go ahead and put the area to the left. Then comma, you need to put some degrees of freedom. So let's try, we have time to do at least like letter A and B. So letter A, example number 3. Using the t-table or the calculator, we're going to use the calculator. Find the critical value t, so find t star for a 90% confident interval if the degrees of freedom is 17. So here's what you'll do. You'll do, I didn't show my work. Okay, so you'll do an inverse t. So get your calculators, go to menu, menu probability, do distributions, and instead of inverse normal, choose the one that says inverse t. Inverse t. Now you have to put the whole area to the left. So if you want 90% confidence, you have to add the bottom tail. So that's going to be 0.95. 0.95. And then you have to put the degrees of freedom. So 17. And that's going to give you what's called your T star. So 1.74. Okay, so you try it again with letter B while I show my work here. Go ahead and try it again with letter B. Equals inverse T. So hopefully you tried letter B. I'll try to show my work. Letter B should be inverse T of 0.99, comma 88. So I got 2.37. And then, okay, you're gonna have to finish the rest of these by yourself. I'll finish the video and then you can just watch like the last 5 minutes, or just go through the PowerPoint and finish the rest of these. Okay, practice doing some Z and T intervals. Okay, let's go ahead and finish the rest of example 3 here. Letter C, you wanted to find the critical value for a 99% confidence T interval with the sample size of 20. So you will have to first find the degrees of freedom by doing n minus 1, so 20 minus 1. That would be your degrees of freedom. So on your calculator, again, it's an inverse T, menu, probability, distributions, inverse T. And although it's a 99% confidence, you still need to add the bottom tail, so 0.995. And then, like I said, the degrees of freedom should be the sample size minus 1. So we'll do 19. And that should give you your critical value T star, 2.86. And then you also need to practice finding p-values that involve a T distribution.
Do we need to use the even odds for it?
Okay, so now we need to find p-values using that TCDF. So on letter D, find the p-value if your T-score is greater than or equal to 2.09 with 4 degrees of freedom. It's called a TCDF on your calculator. So what we'll do is find the probability that T is more than 2.09 by doing menu, probability, distributions. But this time, instead of the normal CDF, you look for the TCDF. And you want it greater than 2.09, comma infinity. And then you still need to type in your degrees of freedom, 4. And that gives you a p-value.
Ms. Garcia.
Okay, so for the last example, you had to find the p-value if you have the absolute value of T. So that means it's like a two-sided hypothesis. So you want greater than 1.78 and also less than negative 1.78. Or just to do it easier, we're just going to find the probability that T is greater than 1.78 and multiply it by 2. I forgot to multiply by 2. Okay, so you just get your menu, probability, distributions, TCDF, 1.78 to infinity. And then this time the degrees of freedom should be 23 minus 1, so 22. And then make sure you multiply your answer by 2 because you have a two-sided. So that's how you get the 0.089. I need to put a little 2 here. Now go ahead and practice. Good luck.